So Bismillahir Rahmanir Rahim. Today we will discuss the Newton's laws of motion. So we start with the Newton's first law of motion. So Newton's first law of motion. So in the previous lecture, we discussed the things that were related to the motion. For example, we talked about the velocity, we talked about the acceleration. But here today, since the acceleration is caused by a force, so today we will talk about the Newton laws, which explains what the force is and what happens when the force is applied on an object. So the first law states that, according to the first law, if there is the net force on an object is equal to 0, the acceleration will be 0, which means if a body is at rest, for example, we have an object which is laying here. If this object is at rest, it's not moving, this object will remain at rest for hour and hour and hour unless there is an external force that is applied on this object. And for example, if this object is moving with a uniform velocity means there is no acceleration. This body is moving with the uniform velocity, a constant speed. This constant speed will remain for hour and hour and hour unless there is an external force that acts upon it. But in the daily life, we can clearly see that everything, whenever something is moving, it stops. It stops because of the resistive forces. There is an air drag, for example. There is a contact resistance. That's why these are actually forces that they are acting on the object to stop the object. That's why we don't see the Newton's first law in action in our daily lives. But if we, for example, ignore all the resistive forces, for example, we ignore the contact resistance, we ignore the air drag, and we go to the space, for example, and there is no resistance. If we keep something at rest, that object will remain at rest for hour and hour and hour. Similarly, if something is moving with uniform velocity or even uniform speed, the speed will remain, the magnitude of the speed will remain, it will not change unless there is an external force that acts upon it. So the Newtons wrote a famous book which is called the Principia, and he explained, or he stated this first law of motion. So I will read what he wrote. So Newton wrote in the book Principia, a body will remain in the state of rest or uniform motion in the right line unless it is compelled to change that state by the forces impressed upon it. So it states that if a body is at rest, it will remain at rest, or if it's moving with the uniform speed, in the straight line, it will always be moving in the straight line with the uniform speed unless there is external force that acts upon it. And this law holds only in the inertial frame of reference. So inertial frame of reference, inertial frame of reference. So the inertial frame of reference means whenever there is no acceleration in the reference frame. So in our previous lectures, when we were talking about the vectors, we talked about the acceleration, we talked about the velocities, we were always describing the motion of for example, something is moving in the random path, but we were always describing this path with respect to a frame of reference. For example, this is our frame of reference, but this frame of reference is not moving and there is no acceleration. So we can This is, for example, the position of vector at time 1, and after some time the position of this object is here. So this is R2, and this is, we can describe this the motion of this system with respect to this frame of reference, and the acceleration is 0. If the acceleration is 0, means the frame of reference itself is at rest. It's not moving, or it's moving with the uniform velocity, and the acceleration is 0. So this type of frame of reference, is called the inertial frame of reference. If, for example, this frame of reference itself is accelerating, then we cannot use this Newton's first law of motion. So the Newton's first law of motion holds only in the inertial frame of reference. Now the inertial frame of reference is when there is no acceleration. For example, the acceleration here, this frame of reference is not moving, is not accelerating, so the velocity is not changing, or it's at rest. So this is the frame of reference. Now we take an example. So there is, for example, a person who is sitting in a car. So we have a car here, and there is a person sitting in this car. So, and this car is accelerated in this direction. So there is an acceleration, and this car is accelerating in this direction, and that's because that the force is applied because of the engine. And the seat, for example, the person is sitting on the seat, and the seat is applying a force and a push on the person, and the person is accelerating, or the whole system is accelerated in this direction. And there is another person who is standing. So there is another person who is standing on a road, and this person is not moving. So this acceleration here is 0. So if we take the frame of reference, means with respect to this person, so if we consider this person as our frame of reference, so this is our x and this is y, and we describe the motion of this object with respect to this person. So this is our frame of reference. So with respect to this person, what this person is seeing, that the car is accelerated towards him, towards this frame of reference. So if there is an acceleration, that means, according to the Newton's first law, if the acceleration is not 0, means there is some force that is acting on this person. So if we ask this person that, do you feel some force? And this person will say, yes, I feel a force from my back, and that's the seat is pushing. The seat is pushing this person because the car itself is accelerated. So this law holds in this case. But for example, now we take the car which is accelerated. So here the acceleration is not equal to 0. And this, we take the car itself which is accelerated in this direction as our frame of reference. If we take our car as a frame of reference, that means, according to, since this is accelerated towards, this is moving and accelerated towards this person which is standing on the road, and he is not moving. If this person is not moving, but this car is moving towards him. So according to, if we take this frame of reference, this person is coming towards him, because we take this frame of reference. Because if the car is moving, so according to this person, if we consider this as a frame of reference, the person is moving towards the car. But if we ask this person, do you feel some force that is acting on you? And that person is not feeling any force, because he is standing there and not moving. So this law doesn't hold that, although according to the car, the person in the car, that person is accelerated. Because according to this frame of reference, which is not inertial and the acceleration is not 0, this person is accelerated. But if we ask this person, do you feel any force? And that person is not feeling any force. So this first law does not hold in the non-inertial frame of reference. It only holds when the frame of reference itself is not accelerated. The acceleration must be 0. Now, everything that's around us is either on the earth or outside the earth. Can we consider the earth as an inertial frame of reference? So we have to look at the earth. For example, right now I am standing here, and with respect to me, this board is not moving right now. And this, with respect to me, the seats in front of me are not moving, or everything that's in front of me are not moving. So can we consider this earth as inertial frame of reference? No, because the earth, first of all, is spinning. So we have the earth, for example, the earth is spinning, and because of the spin there is a centripetal acceleration, and the earth on the other hand is also revolving around the sun, and that's additional acceleration. So that's additional acceleration, and the whole solar system is revolving around the Milky Way galaxy, so that's additional acceleration. So the earth is not, we cannot consider the earth as an inertial frame of reference. Now we will see how much acceleration is produced because of the spin of the earth. Since everything that's happening around us, that's happening on the earth, so we will see that how much acceleration is produced because of the spinning of the earth. So this is the earth, and this is the axis of rotation, and the earth is spinning, and this is the, so this is the, for example, this is the equator, and this is the R, radius of the earth. And now we want to calculate that how much is the acceleration that is produced, that is, if someone is, for example, on the earth standing here on the equator, since the earth is spinning, there must be a centripetal acceleration. So we want to know what is this centripetal acceleration. So this one, so we calculate this centripetal acceleration. So for that we need the time period. So we have the 24 hours, and 1 hour we have 3,600 seconds. So this is in 1 day. So this is the period of the rotation. Period of the rotation means that how long does it take to complete one rotation. So this is the in seconds. So this is in seconds. So we have 24 hours, and in 1 hour we have 3,600 seconds. And the angular speed, so angular speed is represented by, so we will discuss about the angular speed in our later lectures, in the later chapters, but here we will just use the angular speed, the formula here. So if we put these values here, angular speed, so divided by 24, and so this is our angular speed, and the angular acceleration, so this is our centripetal, this centripetal acceleration. We want to know that how strong this acceleration is because of the spinning of the earth. So this is omega square, this is the angular speed, so this is the radius. So if we have the angular speed here, we calculate this one, and we have the radius of the earth. So we have the radius of the earth, that's also known, if we put the values here, so we will get 0.034 meters per second square. So this acceleration, we can see the acceleration due to the spinning of the earth is very, very small. If we compare this acceleration to the gravitational acceleration G, which is 9.8 meters per second square. So if we compare it to this one, so this acceleration, which is this acceleration, the centripetal acceleration, is 300 times smaller than the gravitational acceleration. Since it is so small, we can consider that we can just ignore this acceleration, and then we can consider our Earth, our surface of the Earth, as inertial frame of reference for the practical purposes. Although this is not the perfect inertial frame of reference, but for our practical purposes we can just ignore this very small acceleration. That's why we do not feel this acceleration. The only acceleration, because this one is 300 times bigger than the acceleration due to the spinning of the Earth. So we can consider the Earth as a inertial frame of reference. So now we discuss the Newton's second law of motion. So Newton's second law of motion. So Newton's second law of motion. So the first law was about the system when there is no external force, so or the net force is on the system is zero. But here the second law is about the system when there is an external force, so the net force on a system is not zero. So we take an example. So we have, for example, a wall, and we have a spring. So we have a spring, for example. So this is, for example, a relaxed length. So relaxed length of the spring. So this is a relaxed length, means that whenever we do not apply any force, so the relaxed length or the normal length of the spring will be this one. So this is, we call it a relaxed length. And when we stretch the spring in this direction, so the length will be extended, right? And we attach a mass here. So we have a mass here. So this mass, because of because we have stretched the string, this mass will experience a force in this direction. So this force, the object will be feeling acceleration. So we have, for example, a mass 1. So this mass will, because of this force, this mass will feel an acceleration. We call it m1. So we have the first mass, for example, we have the 5 kgs, for example, and this mass will feel an acceleration a1 because of this force. Now we replace this mass with a bigger mass, for example, and we call it m2. Mass 2. Since this mass is bigger than this one, m2 is bigger than, for example, m1, so the acceleration will be different, and this force is the same. The spring doesn't know what is on the end of the spring. This force is always the same. The spring is the same. So a2. So now it is an experimental fact that m1a equals m2a2. So, and this is equal to force. So this is the Newton's second law of motion. So in simple words, we can write F equals ma. So this is the Newton's second law of motion. What is the unit here? So the unit is here mass. So we have the kg and the acceleration. So we have the meters per second squared, and this is, we call it 1 Newton because of the Newton who described. So this is 1 Newton. Now this law is described by Newton in his famous book called Principia. I will read what Newton wrote in his book. that Newton wrote that a force action on a body gives an acceleration which is in the same direction of the force and has a magnitude given by ma. So whenever, according to the Newton, whenever there is a force that is acting on an object, so he will feel, or this person will feel the acceleration, and this force, the acceleration will be in the same direction of the force. For example, I have an object here. If I apply a force in this direction, so this is the force, so force is a vector, and we will have the acceleration, it is also a vector, so the force and the acceleration will be in the same direction. So this is the Newton's second law of motion. So example is, for example, we have the gravitational force. So for the gravitational force we use G, gravitational acceleration. And this gravitational acceleration is always constant on the, for example, here on the surface of the earth, and if we go up, this gravitational acceleration will reduce. Since this gravitational acceleration is constant, so since this gravitational acceleration here is constant, so this force will be proportional to m. So if we have bigger mass, so we will have, this mass will feel bigger gravitational force. So according to, if we, for example, if I hold, so for example, if I hold this remote in my hands, for example, you can see this remote is not moving. So if this remote is not moving, for example, I have this remote, for example, I just keep it in my hand, for example, here, this is, and for example, the mass of this mass of this remote is, for example, 5.5 kg. So it will feel a gravitational force because of the gravity. But since the remote that I was holding in my hand was not moving, but what we see here, according to the Newton's law, the second law of motion, if there is a force, so we can clearly see there must be a gravitational force that is acting on every object that is on the surface of the earth, or that's close to the earth. But we see this object was not moving. So if this object was not moving, it means that I was applying the same force in the opposite direction. So this was my force, for example, that was exerted by me. So this force and this force were equal but in opposite direction. So they were cancelling each other, so the total acceleration was 0 then. Now what we see here, that the force, the Newton law holds always, and it is independent of the velocity. So if it is independent of the velocity, so we take an example, for example, here. So we have a mass of 1 kg, and this mass is moving in this direction with 50, for example, meters per second, and we have another mass which is also 1 kg. So this is 1 kg, this is 1 kg, and this mass is moving with 5,000 meters per second. So we have same masses, for example, the masses are the same, but they are moving with the different velocities, and there is a huge difference in the velocities. So this is 50 meters per second, and this is 5,000 meters per second. If we apply, for example, 5 Newton force on this object, so 5 Newton force on this object, so for example 5 Newton force on this object and also on this object. So the force will not care at how fast the object is moving. It will just cause, so this is Newton, so this is Newton, 5 Newton. It will just cause the acceleration according to the Newton's first law. So we have the second law of motion. So we have the acceleration equals F by m. So we have the force, for example, force divided by, so we have the force 5 Newton divided by 1, so the acceleration will be 5 meters per second square. So we can clearly see here in this example that we have the same masses, but they were moving with the 50 meters per second velocity, and the second one was moving with the 5,000 meters per second velocity. But when we applied a force with the 550 Newton on both of the 5 Newton on both of them, so the force just ignored the velocity and it just caused the acceleration of 5 meters per second. But if we approach the speed of light, which is the speed of light is represented by c, and it is 3 into 10 raised to the power 8 meters per second. So it is extremely high speed. So according to the Einstein's theory of relativity, if something is moving either with the speed of light or even close to the speed of light, then these equations we cannot apply the Newton's laws of motion, or we can say the Newtonian mechanics or Newtonian physics we cannot use. If something is moving with the speed of light or close to the speed of light, then we have to use the Einstein's theory of relativity. But here we are talking about the speeds. For example, this speed we can say is a high speed, but it's much smaller than the speed of light, so we can apply the Newton's laws here. So now we discuss the Newton's third law of motion. So the Newton's third law of motion, so Newton's third law of motion. So the first law was about the system when there was no external force. And the second law was about the system. It was describing a system in which there is an external, the total net force. But here, the third law is about the contact force, when two objects are interacting with each other. So the third law is describing that system. For example, we have, for example, one box here. So if this box or this object is applying a force on a second object, for example, we have a force here in this direction. So this is, we can say, so this force here is F12, means so this is object 1 and this is object 2. So this force means the force 1 is acting on object 2. So we have a second force. So this object, according to Newton's third law, this object will also apply a same force with the opposite direction. So we will have, this will equal to F minus 2,1. So the minus sign represents that this force is in this direction, we will have exactly the same force with the equal magnitude but in the opposite direction. And this is usually called the action equals minus reaction. So this force here is the action, and then we have the reaction force, which will be minus with the opposite direction, with the minus sign here represents the opposite direction, and the force magnitude will be equal. And now I will read what actually the Newton wrote in his famous book Principia. The Newton wrote that if one object exerts a force on the other object exerts the same force in the opposite direction. So if one object is applying a force in one direction, for example, if I apply a force with my hand on this board, the board will exert the same force on me We can see here, for example, if I apply a force on this board is not moving. According to the second law of motion, there should be an acceleration if there is a force. But since there is no acceleration, it means that the board is exerting the same force to cancel my force. For example, the other example is if you are sitting on the chair, you are applying, so for example, you are sitting on a chair, we have a chair, for example, if your body is applying a force on the chair, that is the gravitational force, mg, and the chair is exerting the same force, means the same magnitude, with the same magnitude but the opposite direction. So the chair will exert the same force, means with the same magnitude, so this chair will exert a force with the negative sign, means the opposite direction. So this is the Newton's 3 laws. So the first law we discussed was about the system where the net force on the system is 0. The second law was about the system where the total force or the net force on the system is not 0, means if there is a force there will be acceleration. And the third system is describing a contact force, and it's about the action and the reaction. So now we will discuss an example in which we will explain or we will try to understand what we just discussed, the Newton's laws, the second law and the third law. So we have a system, so this is the example. So we have a system, so this is the object number 1 and we have the object number 2. So object 2. So if we apply a force, so the force here is 20 Newton. So if we apply a force on 1, the object 1, and this is 20 Newtons. And the mass, so M1 is 5 kgs and M2 is 15 kgs. Now we want to know that how much acceleration will produce because of this force. So we can see here, if we apply a force in this direction according to the Newton's second law, there must be an acceleration which will be in this direction, in the same direction of the force. So this acceleration. And we can also see that there are two objects. So if we apply a force on this object, so this object 1 will apply a force on object 2 to accelerate it in this direction. But this object 2 will also apply a force on object 2. So we will try to calculate those forces as well. So first we use the second law of motion. We want to know what is the acceleration. What is this acceleration? So the Newton's second law. So second law of motion. So that's we have the F equals ma. So we have the ma, but here we have two masses. We have the m1, m2. So we have m1 plus m2 and acceleration. So m1 is 5 kgs and m2 is 15 kgs. So the total mass is 20 kgs. So we have the total mass is 20 kgs, and we know that this force here is 20 newtons. So the acceleration is, we can see acceleration here is the mass here, total mass is 20 kgs. So 20, and we have the force here, we will have the 20, so it's the acceleration is 1 meters per second. So this acceleration is 1 meters per second. So we apply a force on this system, the whole system. So 1 and 2, the whole system is accelerated in this direction because of this force, which is 20 Newton. And now we want to know what is the force that is acting on the object 2. Because if we apply a force on object 1, this object 1 is exerting a force on the object 2. Now we isolate this object 2 and we want to just, so this is the object 2. So this is the object 2 in our case. And so the force that is acting by this object 1 on object 2, we call it F1, 2, means the object 1 is exerting a force on object 2. And we also know, we just calculated, this object 2 is accelerated with the acceleration of 1 meters per second squared. We just calculated that acceleration. So we just calculated that acceleration. Now what we have is the mass and we have the acceleration. So the mass of this object is 15. So M2, we know M2 is 15 kgs. So M2 is 15 kgs. So we know that. So we can use the second law here. So F1, 2 is M2 and acceleration. So it is 15 multiplied by 1, so 15 mass and 1 acceleration. So F1, 2 is 15 newtons. So that we know that the force that is acting by the object 1 on object 2 is 15 newtons. And now we want to know that due to the reaction force, for example, we just discussed if we exert an action, so this was an action, and there must be a reaction force which must be in the opposite direction. So we calculated this force, and now we want to know what is the opposite force. We just want to calculate. It should be the same, but in the opposite direction. And now what we do, we just isolate the object 1. In the first case we isolated the object 2, and now we want to isolate the object 1 in order to calculate the total forces that's acting on it. So we have the object 1 now. So object 1 here. So object 1, we can see there is a force of 20 newtons. So that force here is 20 newtons, that we know, that is given. And this is object 1. And now we want to know what is the force, reaction force by the object 2 on 1. So we have two forces here. So we have two forces there. So we have two forces means, so we use the, so we have the force, so this force plus we have the F21, it must be equal to M1A. So we have the M1 is 5 kgs. So we have the 5 kgs here. So this is kg. So we know this one, this force is 20. We have the 5 kilogram mass, and we have the acceleration that we calculated in the beginning is 1. So we have the 5 minus 20. We will have F21 is equal to minus 15 newtons. We calculated that the F12 means the small object was exerting a force which on the 2 was 15 newtons, and now we calculated that the F2, the big mass, is the big object is exerting the same force with the opposite direction. We just calculated these both are, the magnitude are the same, but the directions are opposite. We have the minus sign here. And now we discuss an interesting example in which we will use the concept of the Newton's third law of motion. And that example is that we have, for example, the Earth. So this is the Earth. So the mass of the Earth is 6 into 10 raised to the power 24 kilograms. So this is the Earth, and we have the radius of the Earth. So this is the Earth, for example, and we have a ball, a small ball, and we drop that ball, and due to the gravity, for example, we have a ball, so small ball. So due to the gravity, this object will come towards the Earth. And now, so the mass of this ball is much smaller than the mass of the Earth, which is here we consider here, for example, we take 0.5 kilogram, which is the half kg. And now this height, so this height here is 100 meters. So now we want to know that how long does this ball will take to reach the surface of the Earth because of the gravity. So because of the gravity, there will be a force mg which will be towards the Earth. And now, so we calculate this one here. So we have the mg. So we have the 0.4, we calculate the force, 0.5 mass, and we take, for simplicity, 10 gravitational acceleration. So we will have a 5 Newton force. So this ball will feel a 5 Newton gravitational force. So this is the gravitational force. Now we want to know how long does this ball will take to reach the Earth. So the distance, this distance is equal to 1 by 2. So we calculated, we derived this formula in our first lecture when we were talking about the dimensions. So this is the distance that covered. So we have the distance that is known, which is 100 meters. So we have the gravity that is also known, gravitational acceleration, which is, for example, we take it here for simplicity, just 10 meters per second squared. So if we put the values, so we will get the t squared equals 20, or the t equals 4.5 seconds. Now what we see here, that the Earth is exerting a gravitational force on this ball, but according to the Newton's third law, this ball should also exert a force on the Earth. So if the ball is moving towards the Earth, the Earth should also move towards the ball. And now we will calculate that how much the Earth will move towards the ball because of this gravitational force. And now for the small ball, for example, we know this acceleration here, which is 10 meters per second. For the Earth to move towards the ball, we have to calculate the acceleration first. So we have F equals ma, the big Ma with this sign. So this is the mass of the Earth. So if we have the acceleration, it will be F by mass of the Earth. So we have the force, which is 5 newtons, we just calculated, and we have the mass of the Earth, which is 6 into 10 raised to the power 24. So if we put these values, so we will get 8 into 10 raised to the power minus 25 meters per second squared. So we can clearly see that the acceleration towards the ball of the Earth is extremely small. This is extremely small. That's why we do not feel the Earth's movement towards the ball. And now since we know that the ball will reach the ground in 4.5 seconds, we want to know that how far the earth moves towards how much the earth moves towards the ball in these 44.5 seconds. So we have the distance, same formula, equals 1 by 2. We have the acceleration, t squared. So t is 4.5, acceleration we just calculated. If we put these values, we will get 8 into 10 raised to the power minus 24 meters. So the earth will move towards the ball by this amount, by this distance. This is extremely small distance. This is much smaller than we can ever imagine to measure. It's impossible to even measure this distance. This is extremely small distance. To give you some idea, the smallest particle or the small particles are the atoms, for example. We take the dimensions of the atom. The radius of the atom is, so the radius of the atom is approximately 0.1 nanometer, which is 1 into 10 raised to the power minus 10 meters. So we can see here atoms are extremely small particles, but the radius of the atom is 10 raised to the power 10 meters, but here this is 10 raised to the power minus 24, which is extremely small distance. That's why we do not feel it. But if we think about it, according to the Newton's third law, the earth is moving with this ball. So for example, if we throw, for example, if I throw a ball upwards, if I throw a ball upwards, means that the ball is moving up. According to the Newton's third law, the earth should go down in downward direction, and when the ball is coming towards the earth should go up. So by throwing the ball or any object up, we are actually moving the earth according to the Newton's third law of motion.